Most of you in this room probably already know who Ray Kurzweil is, and a lot of us wouldn't be here without Ray Kurzweil and his writing. But just in case you didn't know Ray Kurzweil was, he has been described as the restless genius by a Wall Street Journal. Inc. magazine calls him the rightful heir to Thomas Edison. As one of the leading inventors of our time, Ray was the principal developer of the first CCD flatbed scanner, the first omni-front optical character recognition, the first print-to-speech reading machine for the blind, the first text-to-speech synthesizer, the first music synthesizer capable of recreating the grand piano and other orchestral instruments, and the first commercially marketed large vocabulary speech recognition. In 1999, he received the National Medal of Technology, the nation's highest honor in technology, from President Clinton in a White House ceremony. And in 2002, he was inducted into the National Inventors Hall of Fame, established by the U.S. Patent Office. He has received 20 honorary doctorates and honors from 3 U.S. presidents. One of Ray's books, The Singularity is Near, was a New York Times bestseller and has the honor of having been a #1 book on in Amazon on both science and philosophy. So, Ray cannot be with us today in person, but he is teleconferencing in, and he should appear to my screen on the right when I say hi. How you doing, Ray?
I'm good.
Good to see you. How's Massachusetts treating you?
It's good. I'm here on vacation, and sorry I couldn't be with everyone. Actually, sorry for myself, given the really impressive lineup of speakers, which I will listen to the videos when they're available. But I do appreciate this opportunity to share ideas with you today.
Definitely. Are you ready to speak to all these fine people from the other coast in San Francisco?
I hope so. I'll think of something to say.
Well, we hope so too. Fingers crossed. I will let you take it from here, Ray. Ray Kurzweil, everyone.
Well, thank you for that. And I've enjoyed all of the Singularity Summits. It's exciting to have a group of people who do appreciate the law of accelerating returns, the exponential growth of information technology. And I'd like to focus on the brain. Perhaps the primary or most compelling obstacle or criticism of the idea of a singularity is that the brain is too complicated. It's too magical. There are quantum properties that we can't emulate. There's something about the human brain that's beyond the reach of our technology. And I'll show you actually an image that one critic, John Horgan, put in an article saying, look at this. This is an image of the cerebral cortex. And look at the fantastic intricacy of the interconnections. And this is just a small slice of the cerebral cortex. We'll never figure this out. So I was going to have an on-stage dialogue with him, and in preparation I looked up the image, and it turns out not to be an image of the cerebral cortex at all, but actually an image of a simulation of the cerebral cortex. So this audience laughs. I've relayed that to other audiences, and they don't quite get my point. But we have at least figured out the complexity represented by that picture. And one of my arguments is this exponential growth underlying information technology in many other areas is being applied to reverse engineering the human brain. There's several other speakers who will touch on that at this conference. I think it's arguably the most important project in history. Now, it's not actually my view that we would have to do this at all in order to understand and recreate the powers, the intellectual powers, the emotional powers of the human brain. We've actually made very good progress in artificial intelligence without looking inside the human brain. It's only recently that we have the capability of looking inside the human brain, but it will augment very substantially our ability to do this project. In fact, I had a long-standing debate with Tommaso Poggio, who at that time was head of the MIT Machine Vision Lab and also was in charge of reverse engineering the human visual cortex. And I'd say in the early years of this decade, he would say, well, Ray, we're not getting any benefit from understanding the human visual system in creating machine vision systems. And I said, that's because you haven't done it yet. And we did get some information about the early processing in the auditory cortex. We applied that in the 90s to our speech recognition work. It was actually very counterintuitive. After we saw those transformations, we could rationalize why they made sense, but it's not something we ever would have derived on our own. We applied it to speech recognition, got a big boost in performance, and I said that'll happen to you as well. And in 2006, at the AI 50 conference, which was a conference at Dartmouth on the 50th anniversary of the 1956 conference that gave artificial intelligence its name, he came to me and said, you know, Ray, you were right. We just were able to come up with a very good simulation and model derived from these various cues that we got from reverse engineering very specific neurons and looking at the wiring patterns and making a big leap forward in terms of reverse engineering the human visual cortex. We applied that to our machine vision systems. It was counterintuitive, and we made a big leap in performance. So I think we will basically expand our AI toolkit. It's not my view that we're just going to simulate the human brain mindlessly, if you will. I think the whole point of reverse engineering is to understand the principles of operation. What are the basic ideas that the brain is utilizing, that evolution utilized to create intelligent performance that we can find out from reverse engineering the human brain? Then we can take these principles and focus on them and amplify them and leverage them. That's basically what technology does. Consider Bernoulli's principle, which is a very subtle scientific principle that there's slightly less air pressure over a moving curved surface than a flat surface. And in fact, we still don't understand why that is. At least there's still debates in the thermodynamics community as to what the mathematical derivation of Bernoulli's principle is. But engineering, technology took this principle, focused its powers, and created the whole world of aviation. So as we understand some of these basic principles, some of them are beginning to become clear. We can add to our toolkit in artificial intelligence. It will greatly accelerate the path we're on, and it does provide an existence proof. If you look at the exponential pace, there's been tremendous progress just since my book came out, and it does provide an existence proof that we will be able to come up with the algorithms based on this exponential progression. The hardware case, it will have sufficiently powerful hardware, memory, and computations to simulate the human brain or recreate its functional capabilities in real time, is pretty uncontroversial at this point. There are different ways of deriving what that number is, and they actually all come out around the same range, between 10 to the 14th and 10 to the 16th calculations per second. So I've taken the more conservative one. I predicted that by the end of the first decade of the century, we would have 10 to the 16th calculations supercomputers. I was chided that here it is, 2010, we don't have them, but actually IBM is in the process of shipping the Sequoia supercomputer, which will come online in a few months in 2011, and is at 10 to the 16th calculations per second. Moreover, we'll have that for just $1,000 as we get into the 2020s. I think it's been quite clear for some time, even if you don't think Moore's law will continue, and I think that's incorrect. I think every time one paradigm has run out of steam, we've gone to another paradigm. Moore's law, as I'll show you in a moment, is not the first but the fifth paradigm to bring exponential growth to computing. We'll go into the sixth paradigm, which is three-dimensional molecular circuits. Justin Ratner, the Chief Technology Officer of Intel, will tell you, as he has presented at Singularity University, that they have these circuits working in their laboratories. They expect the crossover to be in the teen years. But even if you don't buy any of that, just conventional flat integrated circuits will achieve 10 to the 16th calculations and beyond for relatively modest cost as we get to the end of this decade. And then, of course, there's the whole issue of cloud computing, where we can already harness the equivalent of supercomputers by using all the massively number of unused computers on the internet. At least this argument that the brain's too complicated or has some special properties that we can't possibly emulate with technology is an argument. I'm quite impressed with how little substance many arguments have from otherwise thoughtful people. There are many otherwise very sophisticated people who, for some reason, just will not accept the basic concept of the exponential growth of information technology. Doug Hofstadter is another one, and I started debating this with him about 15 years ago, and I felt, okay, I will keep this dialogue going and show him more evidence. And he's clearly a very sophisticated thinker, but will just never accepts this idea, no matter how much evidence you present, that information technology grows in an exponential manner. Jerome Lanier in the New York Times article recently chides the Singularity community, saying, well, that everybody's very impressed with how apparently intelligent recent innovations in AI are, and then he patiently explains how, but these are really not conscious human beings, and they're not operating at human levels. And I don't know, and it's really setting up a straw man that he then proceeds in his article to defeat. I don't know anybody who thinks current AI is operating at human levels or it represents a conscious person. That's really a straw man. The argument is that these technologies are growing exponentially, and we can measure what the goal is in terms of achieving human levels. They will achieve human levels, and even if you think the exponents aren't quite right, as the previous speaker just pointed out, so maybe it won't be 20 years, it'll be 50 years or whatever, but it's going to lead to some transformation in the future, something singular. He then goes on in this New York Times op-ed piece to describe a whole set of beliefs that the Singularity community has, and then basically scoffs at them without arguing that any arguments in particular are wrong, just kind of sets up this straw man and ridicules it because it sounds too fantastic. I will say that there's really no one view of what the singularity is. In my book, I define a singularitarian as someone who has an appreciation for the fact that information technology progresses in an exponential manner, that's not intuitive, our intuition is linear. The reality of information technology, not all technology, is exponential. There's a huge difference. 30 steps linearly is 30 steps exponentially is 1 billion. That's what we've already seen. This computer is 1 billion times more powerful per dollar in terms of MIPS, in terms of bits of communication than the computer I used when I was an undergraduate. So it's not just a speculation about the future. So there's an appreciation that there's exponential growth, that it's likely to continue. And exponential growth ultimately it's actually continuous. It's soft. There's no discontinuities, but it ultimately leads to some profound changes, something singular. I think that's really where a consensus, if you will, in this field, hesitate to call it a movement, ends. If you were to take 4 people in this audience and ask them a question, you'll get 4 different answers. Maybe you'll get 5 different answers. And it's the same thing that's true in general of this field. How long it will take to achieve different objectives? What are the risks? Are there any? What should we do about it? Should we direct this technology in certain directions? Are there ways to keep it safe? What are the philosophical implications? What is a person? Can a machine be a person? Can a machine be conscious? These are really valid issues. I think if there's any prediction I would make, it's that these issues will become compelling issues and not the polite philosophical debate that they've been since Platonic times. So actually, I was leading up to a question that's been on my mind, which is some people accept this basic notion that information technology progresses exponentially, and they have an intuitive grasp, but it's going to lead to something transformative. And because after that, there's really, as I say, no consensus But some people just reject that notion, and it seems to be an emotional thing. And the arguments from people who otherwise make very sophisticated rational arguments are just emotional expressions. And I've given talks on what those lines of thought are. But the question is, why do some people immediately accept this and grasp this concept and can accept it and actually begin to think constructively, okay, what does this mean? What should we be doing now about it, if anything? And other people really find it impossible to emotionally accept. And I'll tell you some things that are not answers to that question, which is sophistication, education, accomplishment. I found actually junior high school students to be very accepting of this. That's ironic because they haven't been around that long to actually experience this exponential growth, but actually they have been. I mean, just in the few years that they've been using technology, they may be 13 and they've been using it since they were 8, and in those 5 years they've seen such profound changes that they kind of get it. And other people have been around for 50 years and have seen a lot more change than that and won't accept it. I really actually don't have a good answer to that. It's something you might think about. I've been talking to people for many decades now, well, not many decades, a few decades, about these issues. And at first I thought it was just a matter of exposure, but I've really found that some people readily accept it and some people will continue to be resistant. So I'd like to, on that note, very quickly go through some of the information on the law of accelerating returns, but a lot of you have seen this material before. This is a new presentation. We have updated these graphs. The Singularity is near, had the graphs through 2002, since it's a 2005 book. Along the way, updated them a few years. Now they've been updated to 2008 and 2009. They've stayed right on course. But I don't want to dwell on that. I'd really like to say a few more things about the mind, because I'm kind of in the midst of thinking about this now. I think our work on the brain and the mind is the cutting edge of the singularity, and that really the most profound phenomena in the world is intelligence. And biological evolution did evolve intelligent creatures, and we've already amplified that intelligence with our machines, and that's going to go into high gear. And particularly when we can really understand how our intelligence works. And then we can go beyond having a mere billion pattern recognizers in the cortex and a mere 6 levels of indirection and hierarchical thinking and fairly limited topology of connections between the different modules and so on. We don't have to fit it into a 1 cubic foot skull. I mean, a big innovation in human beings, building on Greg Stock's comments, is you had Homo sapiens that had a bigger forehead so we could squeeze in a larger neocortex. That was a big innovation, but we don't have to be restricted to 1 cubic foot. And moreover, we can run it on a substrate that's not sending messages using chemical signals that are 1 million times slower than electronics. So once we understand these principles, we can re-engineer them in a number of ways, which I will try to point out. But let me jump through this quickly. These are some of the points I had hoped to make. So maybe you can just read this and we can jump to the Q&A. So let me, well, I'm going to skip this stuff. I mean, here is, if you jump to slide 16, this is the sort of quintessential graph. I had this graph about 30 years ago, 1980, and it was really the early part of Moore's law at that time. But I was pretty amazed at how smooth a trajectory this was through 2 world wars, the Cold War, the Great Depression. I mean, nothing seemed to have any impact on it. And it had gone through many different iterations. People were already talking about Moore's Law, but this started decades before Gordon Moore was even born. And every time one paradigm ran out of steam, it went to another one. This logarithmic graph kind of squeezes the level of progress because every level on this graph is 100,000 times greater than the level below it. So this represents trillions-fold increase in the number of MIPS per dollar, bits of communication per dollar, since the 1890 American census, a billion-fold just since I was a student. Then I updated it from my 1999 book, The Age of Spiritual Machines, and it appears in there. I updated it again through 2002 in The Singularity is Near. I've updated it a couple of times since then. This now goes to 2009. And it continues right on pace. It's amazing, actually, that you get these very predictable trajectories. What you're measuring here, it's not like thermodynamics where you're measuring some natural process. You're measuring human innovation, creativity, competition, entrepreneurship. You would think that would be very unpredictable. Indeed, it is unpredictable. In fact, thermodynamics is unpredictable because if you look at the mathematics of thermodynamics, it models every particle as following a random walk. But then through the statistics of large numbers, even though you can't tell where this particle will be 10 seconds later, the properties of the entire gas are very predictable to a very high degree of precision, according to the laws of thermodynamics. It's the same thing here. Any particular project is very unpredictable. You would have had to have great individual personal insight to know that Google would be the winner of the search wars some 12 to 15 years ago. But the fact that the technology was emerging to create the basis to make search engines feasible, that was predictable. And out of all these millions of individuals and projects and companies around the world, you get this very predictable trajectory that belies our intuition. And I mean, there's many different ways to look at electronics, which I won't dwell on here. Average transistor price coming down very smoothly. Again, the most remarkable thing about this is look at how smooth the trajectory this is, how predictable it is. We've gone from one transistor in 1968 per dollar to $1 billion today. And they've sped up, and so the cost of transistor cycles come down by half about every year. That's a doubling of price performance. It's a 50% deflation rate. But it actually, ironically, fuels economic growth because we more than double our consumption as measured in MIPS or bits. So it actually provides 18% growth in constant currency per year, despite the fact that you can get twice as much of it each year for the same cost. Magnetic data storage, I just put that up because it's not Moore's Law. It's a different engineers, different problem. And biotechnology, you'll hear a lot about that. You just heard Greg Stock's presentation on that. We actually see in biological evolution this acceleration because DNA took on the order of 1 billion years to evolve, and then the Cambrian explosion went 100 times faster, and evolution of Homo sapiens went 100 times faster than that. But the growth in the amount of data we're sequencing, the cost per base pair, all of which is progressing at an exponential rate. And there's many other ways to measure these biological technologies. So biology, health, and medicine, which was not an information technology, it was hit or miss, and therefore it did not progress exponentially. It did progress linearly. That's still been useful. When I talked to these junior high school students recently, I told them you'd all be senior citizens if it hadn't been for the progress we made since human life expectancy was 23 1,000 years ago. It was 37 in 1800. But that's linear growth. Now it's an information technology. We not only have the solver of life, we can change it. RNA interference can turn genes off. New forms of gene therapy can add new genes. We can design these interventions on computers. We can test them out in biological simulators. Communication technologies, many different ways of measuring this. I saw the DARPANET doubling in power every year in the early 80s, predicted a World Wide Web, tying together hundreds of millions of people emerging in the 90s. People thought that was nuts. when the entire U.S. defense budget can only tie together 2,000 scientists in a year in the early 80s. But that's the power of exponential growth. We're shrinking technology, and that's also an exponential progression. But let's talk more about the brain and also the mind, which is a very similar phenomenon. And if there's a difference, it's a pretty subtle one. Perhaps in the mind we would throw in our sphere of consciousness of what we're aware of. So our body would kind of fall into that. But actually we're aware of some parts of our body more than others. And it brings up the whole issue of consciousness. And I do want to come back and talk about that. It's a very difficult subject. Invariably, when people talk about consciousness, they somehow fall into some objectively measurable performance, which is really not the hard problem of consciousness that Chalmers has described. The hard problem of consciousness is ultimately so elusive that you can't measure it at all. It comes down to actual conceptual gap between the nature of subjectivity, which is the definition of consciousness, and objectivity, which is a synonym for science. But this exponential growth of information technology is pervading our understanding of the brain. And it's the nature of exponential growth that you start out kind of doubling very small numbers. Technology is not very effective. It gets to a point where it really begins to take off. That's been the case only recently in the area of reverse engineering the brain. As of a few years ago, we really could not see inside the brain with sufficient resolution to see what was going on. The state of the art was fMRI. Someone looks at a loved one, this area lights up, they solve a logic puzzle, some other area lights up. It kind of tells you where things are happening, but not with enough resolution to actually understand how it works. But now the spatial resolution of brain scanning, which has been doubling every year, and the amount of data that we're gathering is doubling every year, allows us to actually see in a living brain, a living human brain, individual interneuronal connections, see them firing in real time, seeing them be created in real time. We can see our brain not only create our thoughts, but we can see our thoughts create our brain. We do have that plasticity. It's part of the paradigm of human intelligence, that as we think about something, we are creating brain matter that reflects that subject matter. And we very literally create our brain. We create who we are by the thoughts we have. Thoughts seem very ephemeral, but it turns itself into physical brain matter. And we can actually see that now. The most important region is the cerebral cortex. This is that image that I mentioned earlier that John Horgan cited in his article in IEEE Spectrum magazine. And this is actually a simulation, an image of a simulation of the cortex. And we have reverse engineered enough of the cerebral cortex to understand some basic principles of its operation. Not enough to fully master it, although there are projects that claim to be scaling up exponentially, like the Blue Brain Project. I was actually on a panel in Israel with Markram, the head of the Blue Brain Project. I was actually the conservative, because I was saying we're not going to reverse engineer the human brain until the end of the 2020s, and he was saying he expected to do that by 2018, based on the pace with which he's scaling up this cerebral cortex simulation. And I said, well, you may, at some level, scale up a simulation by that time, but I don't think it's going to work, actually, by 2018. You're going to have to iterate on the design, and we're also going to have to teach this simulated cerebral cortex some knowledge, because that's part of the human paradigm. If we, in fact, succeeded in completely successfully simulating a human cortex at human levels and beyond, and it was absolutely a perfect simulation, it wouldn't do anything until it learned something. That is part of the human paradigm. Now, it doesn't mean we have to spend 20 years educating it the way we do biological brains. We can accelerate that process as well, but that's actually maybe the most challenging engineering project in creating an artificial brain. One of Horgan's other criticisms is it would take trillions of lines of code to simulate the human brain. And he points as evidence the number of connections, which are in the hundreds of trillions. And he does the math and says it would take trillions of lines of code. And so my first response is, where are these hundreds of trillions of lines of code? The design of the human brain is in the genome. And that's the only place that there's any design information. And I do the analysis in singularities near. There's 800 million bytes of information, 3 billion rungs, 2 bits per rung. So even including the non-coding DNA, which used to be called junk DNA, which we now know does have a influence on gene expression. So assume it's all valuable. That's 800 million bytes, but it's replete with redundancies. One sequence called ALU is repeated 300,000 times. So if you have redundancy, you can use lossless compression. Do the analysis. I come up with about 50 million bytes after lossless compression. Of all the DNA, only 3% of which is coding. And so that's about 1 million lines of code, and about half of that describes the design of the brain, not trillions of lines of code. Now, how could that be? How can you have 1 million lines of code describe something that has trillions of connections in it? Well, that's not hard to understand. There's obviously some redundancy. We have reverse engineered the cerebellum, which is where we do a certain part of our skill formation, like catching a fly ball or walking. I mean, that's done by the cerebellum. And there's one structure that involves a number of different types of neurons. We understand that structure, and we actually understand how it processes information. And it's repeated 10 billion times with a fairly simple wiring pattern. And there's some random variation with each repetition within certain constraints. That's what the genome says about the cerebellum. And it's actually a few tens of thousands of bytes, even though it involves trillions of connections. The same thing is true of the more important cerebral cortex. Now, the cortex is the only region that allows us to think in hierarchies. So we can think of a whole bunch of symbols, and we call that an idea, and we give it a symbol. And now we can use that symbol with some other symbols and create another complex idea and call that an idea and give that a symbol. And we can keep doing this nested structure and create a whole hierarchy of symbols, which we call knowledge. And only the cerebral cortex allows us to do that. And only mammals have a cerebral cortex. So a lizard really is not able to think in this hierarchical manner. There are some ways in which it can process information that are well-tuned for its particular ecological niche, but it's really not able to create anything we would call knowledge or have insights as to how one idea applies to another, and so on. And the big innovation with Homo sapiens is we basically, as I said, have a bigger cerebral cortex. We have this big forehead that allowed the cerebral cortex to expand. It's the size of a table napkin. In a mouse, it's the size of a postage stamp. In most primates, it's the size of a number 10 envelope. We have one that's the size of a table napkin, and about the same thickness. It's a flat structure. And it also has a lot of repetition. It has 1 billion units, and these units, these modules, are pattern recognizers. They recognize patterns. And so there's a set of modules in your cerebral cortex that have learned, for example, to recognize a pattern of a crossbar and a capital A. And there's more than one of them, because there's many different ways to look at it, and you've got a whole bunch of these modules that have devoted themselves to understanding capital A crossbars. And then you have other modules that are higher in the conceptual hierarchy that can recognize, say, irony or humor, and they're much higher in the hierarchy of ideas. But interestingly, they're actually pretty much the same type of module. They are connected at a higher level of the conceptual hierarchy. They have more abstract concepts coming into them as inputs, but they're actually organized pretty much the same way. It's not clear there are any differences at all. There may be small, subtle differences, but they're basically the same thing. Now, you'll have recognizers that recognize faces. And so you would assume that these recognizers, since they can deal with certainly two-dimensional images or three-dimensional images or subtle, very abstract concepts like irony or anger or humor, pity, must be able to deal with very complex multidimensional structures. Interestingly, though, they're organized as one-dimensional lists. Each one can handle a particular list of ideas in an ordered manner. It's one of the reasons you can say the alphabet forward but not backwards, because they are actually in a forward order, and that's the only way we remember them, unless we develop new ones by studying the reverse order. And that's kind of surprising, but it turns out, I mean, if you go back, for those of you, at least contemporaries of mine, if you remember in the 70s and early 80s, there was a lot of excitement about the Lisp companies, and Lisp was a language, it stands for list processing, and each statement in Lisp is a concept based on an ordered list of other concepts. And because you have hierarchies of concepts in other languages, in C you can have nested functions and they can refer to each other, but it's very pure in Lisp to actually define every concept as an ordered list of other concepts. And you can actually refer to a concept in its own definition. So you can use recursion, which is a particularly powerful method, and our own cerebral cortex can deal with recursion. And there's a lot of excitement in the Lisp community that Lisp represented the way the human brain really works, and it was considered a lot of hype. And ultimately, the Lisp business phenomena kind of blew up. It was kind of the forerunner of the dot-com explosion. Interestingly, this boom-bust psychology is an accurate harbinger of what ultimately is a profound transformation, because people don't actually have the timing correct. The internet was growing exponentially, e-commerce was growing exponentially, and so all these values in the dot-com industry exploded in the late 1990s. And then Wall Street came back around the year 2000 and said, gee, it hasn't changed everything. It hasn't changed anything. I guess we were wrong and all the values went the other way. Meanwhile, it was progressing exponentially, and now we have dot-coms like Google. They're not called dot-coms, but that's what they are, with $20 billion of real revenue and $150 billion of market cap, and there are many other companies like that. The same thing, actually on a longer time scale, is happening with AI. AI is already tens of billions of dollars of revenue of narrow AI, and ultimately will be trillions of dollars of revenue. But there was a bust in the business community in the 80s, led to something called the AI winter. But the conceit of the Lisp community and the devotees of Lisp was that Lisp represented how the human brain really works and really deals with concepts. It turns out that they were right, even though we had no information at that time about the cerebral cortex. That is exactly what the cerebral cortex does. Each of these modules in the cerebral cortex, and we have about 1 billion of them, is a Lisp statement. It's a sequenced order of symbols. And the symbols come from other modules which are processing input from yet other modules, and they're all organized in a fantastic hierarchy. The input from one module can feed back on each other, so we can actually handle recursive ideas, which gives us a lot of power. But basically, the cerebral cortex is a Lisp processor. And we can actually, and this was one of the claims of the Lisp community, that even though it's a one-dimensional list of symbols, you can create any kind of abstraction, including two-dimensional and three-dimensional. or n-dimensional concepts of any degree of complexity by building concepts on top of each other. And we have a pretty good idea, actually, about how these modules work. And there are actually a number of different simulations of these individual modules. A trickier issue is how are they wired together. We're beginning to get that data, but that's still incomplete. But I think we can see how we would like to wire them. And the wiring actually is a limitation, not a strength of the human brain. Yes, we create new connections, but we can't arbitrarily create a connection. If you have a module here and literally physically another module is 2 inches away, there are long-distance axons that can tie one module to another, but you can't grow an axon for that amount of time, that amount of length. That's just a limitation of our neural architecture. So you have to harness one that's already there. It may be in use for something else. It's one of the reasons that we don't easily create new concepts. We can't tie every concept to every other one. Certainly if we were to sit down and actually engineer this, we wouldn't put in those arbitrary limitations. But some of the limitations and the way in which the wiring works are important to some of the fantastic powers of the human brain, and we need to understand that. There are many efforts to scale up an understanding of the wiring of the cerebral cortex. There's obviously a tremendous amount of redundancy. There isn't genetic information describing every wire, every interneuronal connection in the cortex. There are theories about exactly what that information is, but that remains to be completed in terms of actually reverse engineering this wiring diagram and then to simulate it. So if you wanted to actually simulate a cerebral cortex, or a brain, which is the goal of a number of projects like the Blue Brain project, you would want to build one of these modules. I think there you don't have to follow the biochemistry. You really need to understand the principles of operation of what is it trying to accomplish, and then developing software that actually achieves that, regardless of how the human brain happens to do it. We want to understand the wiring between these billion different modules, just so we understand what the principles of operation are. But then we can actually do virtual connections much more powerfully and overcome some of the limitations that human brains have. And of course, it can then operate on a substrate that's not sending signals at a few hundred feet per second. There are some other modules in there that account for our human nature and human behavior, things like the amygdala, which deals with a large part of our emotional response, and the mirror neurons, which give us empathy to allow to understand that other people may be feeling the same thing as we are, or that we can feel what they're feeling. The spindle cells, which are unique cells that are only actually in higher apes and humans. We have 88,000 of them. Apes have about 8,000, and they're more in the right brain than the left, and it may account for why we consider the right brain to be more emotional. They're very complex cells with hundreds of thousands of connections. They're very big cells that span the entire brain, and those cells light up when you think of something very emotional. You look at a loved one or hear about some emotionally distressing situation. These are the cells that light up. They create new types of patterns that we then deal with in the cerebral cortex. That's where we do our thinking, but it's the other regions that basically provide our motivations and our goals and so on. So you'd need to understand that, or maybe you don't want to understand that, because a lot of these machines are going to be created for very specific purposes, just like we create AI now to solve specific problems. So we may want to provide motivation for AIs very directly to do certain tasks. Of course, what we want AIs to do in the future is a whole important issue that requires more than technologies. And just to touch on consciousness, because people assume that, actually people make lots of different assumptions, but it's very hard to have a pure discussion of consciousness because of this conceptual gap that I mentioned between subjectivity and objectivity. But I'll mention one insight I've had as I've read sort of through the literature in this field, which I've actually been interested in since high school. And occasionally I'll read an article, like recently some articles by Penrose and Hameroff and others that say, okay, we can actually explain how consciousness works. And I get very excited because I've been wondering about this for 50 years. And take, for example, Hameroff's recent paper on cellular computing in the tubules, claims that this certain type of cellular automata in the tubules, and that this has something to do with consciousness. So the whole paper goes through in a lot of detail describing how the tubules could be doing cellular computing and what the evidence is as to why that's taking place. And personally, I actually was not convinced by that. I don't think there's actually useful cellular computing in the tubules. But buried in this fairly technical paper, there's a line that says, we think this is the source of consciousness. And my feeling is, whoa! I mean, this is a fantastic leap of faith that's been taken with no justification. I mean, maybe it's the source of consciousness, maybe it isn't. There's no evidence, or even evidence that you could imagine existing. And what kind of evidence would there be? I mean, there's one piece of evidence, which is that certain indications of the cellular computing don't take place during anesthesia, but there's lots that doesn't take place in the anesthesia. This whole process I described of hierarchical thinking doesn't take place while you're under anesthesia. So maybe that has to do with consciousness. I think that's actually a better bet. There's Penrose's theory that there's quantum computing going on in the tubules, and that counts for consciousness, and there's kind of a attraction to that because consciousness is mysterious, and so is quantum computing, and so maybe they're related to one another. There are theories of gamma symmetry, a certain type of rhythm between the different neural processes, and that's the source of consciousness. But there's really no evidence provided, nor could you even imagine what that evidence would be. And in my view, it's really not a objectively measurable phenomenon. I don't think you can build a device that would measure consciousness where you could have a falsifiable experiment that would make this a scientific proposition. Even without having done the experiment, I can't imagine what that experiment would be. You can measure certain objectively verifiable tests, like does this entity pass the Turing test? That's not a test of consciousness. We can argue philosophically that if something passes the Turing test, we would believe that it's conscious, but it's not a direct measurement of subjective experience. So critics like John Searle call me a reductionist, saying I'm reducing the glory and mystery of consciousness to something computable. But ironically, Searle says that consciousness is just a biological function like lactation or digestion, and once we figure out what that function is, we can recreate it in our machines. So it seems to me, who's being the reductionist? My view is it's actually not something that's scientifically demonstrable. So some scientists go on and say, yes, it's not scientific, therefore it's not real, it's an illusion. Let's just not waste our energy on it. That's not a good idea in my view either. I would not be so quick to throw out the concept because our whole moral system is based on consciousness, and our whole legal system is based loosely on our moral system. So I can't cause suffering or extinguish the consciousness of someone else. I can't cause suffering to a conscious being. But I can destroy some property, maybe not your property, but that's because it causes suffering to you, the owner of the property, not to the property itself. So we really need to understand who and what is conscious. And in my view, that takes a leap of faith. The chapter that I deal with this in my new book is called You Gotta Have Faith. And, okay, there's been faith-based arguments along these lines for many years in the religious traditions. Some supreme being bestows a soul, consciousness, which I think they're pretty much the same thing, on certain entities like humans. In some traditions, maybe animals are included. And then they're stated, this is a article of faith. This is a leap of faith. That's actually at least consistent, because that's actually what it is. So some people say, well, I'm not just going to act by faith. I'm going to act entirely by science. But in my view, this is not scientifically penetrable, because I can't imagine I don't think we can define a scientifically falsifiable experiment that would demonstrate definitively subjective experience in another entity. And moreover, I don't think we could get up in the morning if we didn't take some leap of faith. Every one of us has made a leap of faith. Most people have not bothered to think about what it is and don't bother to articulate it. They just have it in their minds. We all have some idea about who and what is conscious. And generally that consensus includes thinking that each other is conscious, but even there's things that aren't clear. What about people that are sleeping, that are under anesthesia, that are in a coma, that are minimally conscious? How about animals, higher level animals? How about low level animals, spiders, paramecium? Who and what is conscious? Different people have different ideas about them, and in fact, they don't agree. It's the whole issue underlying the animal rights movement is, are animals conscious, or are they just sort of machines operating by some instinct, which is some primitive machine-like reaction? So in my view, we actually have made a leap of faith, and I will articulate, and I don't have time to do it now because I want to leave some time for questions, what my own leap of faith is. But I'll just in a moment say it's kind of the quacking duck theory, that if it quacks like a duck, then it is a duck. Meaning, if it seems conscious, we will believe that it's conscious. Right now, you can have AIs and virtual characters, say, in a video game, and they say, I'm angry, I'm happy, but we don't believe them. They don't have the subtle cues that are convincing. Once they do, once they're really convincing, and as another way to say that is once they pass a valid Turing test, I believe we will believe, and I will believe, that they are actually conscious beings. So let me just finish up. I mean, here's this visual model that Poggio had come up with, showing that the visual stream is broken into 7 different movies, and they're very low resolution movies. Our brain only gets a few cues, despite the fact that there are billions of bits of information streaming from our eyes, and that's all that our brain ever sees. So when we actually think we're seeing something, we're actually hallucinating it in our brains based on very subtle, low bandwidth cues that ever reach the brain itself, or the rest of the brain past the visual cortex. Here's a block diagram of the module that's repeated 10 billion times in the cerebellum. This has been modeled and simulated. We are making exponential gains in understanding our brains. This will ultimately lead, and I don't think it'll be a project we'll ever completely finish, but we haven't finished our understanding of Bernoulli's principle. It didn't stop us from creating the whole world of aviation. We will understand enough about the brain to basically continue this process of amplifying who we are. This makes me smarter. I'm much smarter than I was 20 years ago because I have access to all of human knowledge with a few keystrokes. And ultimately, my computer used to be across campus. Now it's on my belt. Ultimately, it's going to go inside our bodies and brains. It's going to make us more of who we are. That's actually what's unique about the human species. We go beyond our limitations. We've extended our physical reach, and we are now going to extend our mental reach by merging with our tools. Thank you very much.
Ray will now be taking a few questions. We only have one of the microphones up and running, as you'll see, because we want Ray to be able to see the people he's interacting with. So if you please form a single file line at the front. Thank you.
I agree with what you say about the physics of consciousness in terms of Penrose and Hameroff, and I also agree with you that so far there's no quantitative experiment that can measure consciousness in a machine or even in a person. However, there is the possibility of that in a particular interpretation of quantum theory due to David Bohm, in which what's called the hidden variable quantum potential approach. And the idea is basically that the quantum wave function is an intrinsic mental field which satisfies David Chalmers' criterion for physics of consciousness in his Scientific American article in 1995. And this can be worked out. There's also, it can also be shown that quantum theory, orthodox quantum theory, does not allow any conscious phenomenon, which is kind of what David Deutsch at Oxford has said, and I agree with that too. But there is now the possibility of quantitative modeling, which could lead in principle to an experiment and to allow us to determine whether a particular machine, probably at the nanotechnology level, could be conscious in the same way we are. And what it has to do is basically ordinary quantum theory as it's currently formulated, the quantum potential field acts on the, say, the electrons, but without any direct back reaction of the electrons back on the quantum potential. If you could have this, if you could close that feedback loop, changes in the quantum potential would produce qualia consciousness. So that's, in terms of you, I think you're a little bit too pessimistic, although I agree with your assessment of the factual situation.
A couple of things. I've not rejected the idea out of hand that there may be some new insight that would enable us to solve this issue, how we can actually measure consciousness. And yes, you're correct. Certain interpretations of quantum mechanics imply a role for conscious observation, and you can then flip those equations on their back and actually use certain functions like collapse of the wave function to indicate a conscious observer. But there's actually no way, no falsifiable experiment to prove those particular theories. There are other ways of looking at it, that the wave function does not actually collapse. It just appears to collapse because of the interaction with the measurement apparatus. But I think your points are well taken. It's definitely an area worth continuing to look into. I view it as sort of peeling an onion. I mean, there's more and more insight. By the time we're done peeling the onion, there may be nothing left of the onion.
Hi, Ray. Bob Blum here. I want to share with the audience a wonderful paper that's free and online by Anders Sandberg and Nick Bostrom. I'm sure you've probably seen it, Ray. It's their paper that emerged from, I believe it was a small conference that they hosted at Oxford on whole brain emulation, and took place about 3 years ago. And what at the heart of the feasibility of whole brain emulation is the level of detail that needs to be replicated in order to achieve parity with human cognitive function. Is it at the whole circuit level? Is it at the cellular level? Are ion channels required? Do you need to throw in macromolecules and detailed synaptic anatomy? And what's your sense on that, Ray? I think it's basically an empirical question, but you've got an intuition for it that I'd like you to share.
Well, I think it's a great question. I think at this point, if you look at the reverse engineering field, it's being pursued in many different ways. There are people studying individual neurons that are in a petri dish and alive, and they're studying exactly what it does and how it interacts. And there are models and simulations at many different levels of detail. In my view, we should pursue all of these because they're all providing hints. And And the objective is is not necessarily to build a grand simulation where we simulate an entire brain at a certain level of detail. That may be useful at some point as a scientific project, but the real objective is to understand the principles of operation. And I actually don't think they'll be that complicated to explain. As I said, there's only 25 million bytes, which is maybe 500,000 lines of code equivalent in the design of the human brain. I think even a lot of that has to do with just supporting the sort of biological functions for life support of these different neurons and their physical layout and so on. I don't say the brain is simple, but I think it's a level of complexity we can understand. And I think ultimately we will come to an understanding along the following lines. So in the cerebral cortex, we have these modules. This is what the module does. We can then program that module to do that function without completely disregarding neurons and ion channels, and just perform the pattern recognition, list processing capability of that module, and use our best programming and probably do a better job than evolution did. And then they're wired together in a certain way. And that we're still learning about, but there's certain principles of operation about how that works. And we'll find actually there are some practical limitations because there was no wireless communication, other than maybe there is some field effects and EMF phenomena going on, but basically there are discrete connections, and there's some topological requirements for that and real limitations. In a computer, you can create virtual connections and have much more flexibility, but you don't want too much flexibility because unless you understand the principles of operation, it won't work. So I think we're going to get ultimately an understanding along these lines and then build a system that physically is quite different. It's built on a different substrate, obviously, but just the way Poggio went on to take the understanding of the transformations being done in the visual cortex, and then he just had his best programmers program those transformations completely differently than the way they're done in the brain, but it gets the same result. And there's one more thing we're going to need to do, which I alluded to before, is to educate this AI. Part of the paradigm of human intelligence is education. It's quite integral. It doesn't come equipped with any of these hierarchies. It's a Lisp processor with 1 billion Lisp, support for 1 billion Lisp statements, but there are no statements that we start out with, so we actually have to learn them. And we have a certain process, and there's a lot of debate about how to do that with biological brains, but we're going to want to do that more quickly. And it brings up an issue about the turnaround time. So you create a simulation, maybe you've got some details wrong, so it doesn't work, so that you've got to test it, you find out it's not quite right, you iterate, and then create a better simulation. But how do you know it doesn't work? If you then have to educate it, even if you do the education, let's say, 20 times faster than biological brains, you can educate it in a year. That's a long time to find out that actually your simulation is wrong. So that cycle of iterative improvement is going to be difficult if the educational process is part of the evaluation. So these are some of the challenges. But I think ultimately we want to actually understand what's going on. Then we can kind of throw out the details and re-engineer it.
You mentioned the brain scans and the resolution getting better. And I was wondering if you thought that scanning an entire human brain to the molecular level would be necessary first before we could build a strong AI, or if it could be accomplished sooner with another technique like evolving a neural network with genetic algorithms.
We're nowhere close to being able to scan entire brain at the molecular level. We can scan individual neurons or analyze them at the molecular level. We can get somewhat above that level by looking at networks of neurons. So we can get hints by looking at small systems at very fine detail, like the molecular level. I think when we actually scan the whole brain, we're looking more for the connections, because we don't have to to scan every single neuron, because we know that all the different neurons of a particular type are going to be very similar. So once we understand how that neuron works, we're really interested in what its connection pattern is and how it forms new connections and so on. So we're operating at different levels of specificity in order to gain this insight as to how it basically works. We already have a grab bag of techniques. You mentioned two of them, neural nets and genetic algorithms, and evolving a neural net with the genetic algorithms is a very good idea. The neural nets that are used in the human brain are actually, based on what we've learned just in the last few years, are quite different than the classical neural nets used in the neural net field. And I think actually we'll be able to create better neural nets by emulating the type of neural nets we're finding, particularly in the cerebellum, in the cerebral cortex.
Thanks.
All right, guys. Unfortunately, that's all Mr. Kurzweil has time for today. Thank you for coming up.